So this is the recording on the block for this problem, and I prepared something for it. And I'm going to read this here. A 3.0 kilogram block is placed between two horizontal springs. Neither spring is strained when the block is located at the position labeled x equals 0 meters in the drawing. The block is then displaced a distance of 0.07 meters from the position where x equals 0 meters and released from rest. A. What is the speed of the block when it passes back through the x equals 0 meter position? And B. Determine the angular frequency omega of this system. So I'm going to run this animation here first. First of all, I put in the correct numbers. As you can see from the drawing, 450 Newton per meter is the spring constant on the left. 650 Newton per meter is the spring constant for a spring on the right, and then this one here has a mass of 3 kilograms, as you can see. And then I put it actually initially at 0, and the distances to the right and left are arbitrary, and when I put these springs in, when I first put them in, they were neither compressed nor stretched, so there is no force on them. And indeed, when I run this one here, you can see that the position doesn't change and that the velocity doesn't change, so the block is just sitting there. So I'm going to make the more interesting case of actually pulling it out 0.07 meters. And you perhaps saw it shift a little bit, and then there it goes forth and back. And there's a simple harmonic motion. You can see the distance x that it moves forth and back, positive to negative, and you can see the velocity with which it moves forth and back. And here we can kind of estimate its velocity as in meters per second, 0, 1, 2, a little bit more than 1, kind of in the neighborhood of like 1.3, 1.4 meters per second is the maximum velocity. And if I correlated this one here with the position, then we could see that each time x equals 0 is when it hits the maximum speed, either in the positive or in the negative, depending on if it's at that point moving to the right or the left. So somewhere around 1.3, 1.4 meters per second would be the answer to part A. Okay, so let's calculate this. Again, I left this one here open because there are quite a few variables in this chapter that we would have to see what actually we need and what we have to figure out. Of course, what we do have to figure out, I'm going to use a different color here, is omega at some point. That's what they're asking for. And they're asking for the maximum velocity. Let's see if they say that. What is the speed? They don't say maximum velocity. I'm just going to write v. But we can see that as it goes through the 0 position, that's where the maximum velocity would have to be, and that's what they're asking about. Anyway, just one little thing, there shouldn't be a check mark, there should be a question mark. So that's what they're asking for, and that's what they're asking for. What they tell us is the amplitude. What they tell us is the mass of the block. What they tell us are the two spring constants. Okay. Let's see, one equation that we could use is for the angular frequency given as omega equals the square root of k over m. There we go. And then k is the spring constant of one spring. Well, here we would have to see, is that really true, because we actually have two springs coupled together. So I'll revisit that in just a moment. Actually, that's kind of where I'll start out. But let me write down what the velocity is. The chapter gives us this equation for the maximum velocity. And as you could see in the drawing, the maximum velocity does appear, I'm sorry, not in the drawing, but in the animation that I showed you, does appear when the position is 0, and that's what they told us in the problem. So that maximum velocity is amplitude times omega. So once we have calculated omega, then we just plug it in here and we come up with the maximum velocity, which means actually I'll start out with part B. However, first of all, I have to see if this is really true here, if this k here is applicable, again, because we have two spring constants given. What I do in that case is I look at Hooke's law and I write down F equals negative kx. And now I look at this one here. This is the initial position, so it's being pulled a little bit to the right, which means that this spring is stretched, and as it's being pulled to the right, well, the string likes to pull it back to the left, so in the opposite direction. And then this string here, this spring is compressed, and as it's being compressed to the right, it likes to push the block back to the left, and of course Hooke's law says exactly that. The restoring force is always in the opposite direction, so both of them apply F equals negative kx, and we have two forces given. So what we have is F equals negative k1 x for the first spring minus k2 x for the second spring, or plus negative of that. But these are two spring forces acting on the block. The x is the same for either one of them because the amount taken out is the same. And now I can write it as such: minus k1 parentheses plus k2. Notice I took the k2 in the parentheses, leaving the negative outside, and then I have an x outside. Okay, actually had to interrupt my drawing here. I must have hit something strange. In any case, this one now looks the same as the original Hooke's law, and therefore the k is k1 plus k2, those coupled springs. So, as I said earlier, I do part B first because I do need the original. I do need to figure out the angular velocity first. So that's going to be the two spring constants added together, divide by the mass, take the square root, and this one was supposed to be a k. So I put the 450 in here, then the 650, and I divide by 3, and then I take the square root, and then I'm going to come up with the angular frequency, which would have to be in radians per second. And then that result I'm going to plug into the Vmax, and here I can just, whoops, I just wanted to grab the first part. I'll write it down again. So Vmax equals amplitude times omega, and the amplitude of course is the 0.07 meters, and then I'm going to have that result in meters per second. They're asking for the speed, which means keep it as a positive number. And of course the maximum velocity is either positive going to the right or negative to the left, and that's why I keep it, the speed, as a positive number. And as I said earlier, the animation showed that I come up with like 1.3 or 1.4 meters per second, and when you calculate that you will come up with something really close to that.